Hello friends, welcome to our YouTube channel Design in VTU, where we help students to understand and apply design concepts in a more simple and systematic way. Here we are with a new video on design of shafts. Today we will solve a typical shafting numerical. So let's get started. First of all, let us note down all the given data. Here the given data is a pulley of 500 mm diameter is placed at 200 mm distance to the right of the left hand bearing. So let me mark the left hand bearing here. So this is the left hand bearing and this is your right hand bearing. And this drives a pulley directly below it with the help of belt having maximum tension. So this is your pulley 1 and this is your another pulley P2. The pulley weighs 1000 newtons. The weight of this pulley WP1 is acting downwards. Another pulley of 300 mm diameter placed 300 mm to the left of the right hand bearing. So that is the case, and which helps with the help of an electric motor. So this is your electric motor, which is placed horizontally to the right when viewed from the left bearing. So when viewed from the left bearing, so this electric motor is directly in front of the second pulley, and this pulley weighs 500 newtons. So the angle of contact for both the pulleys is 180 degrees and coefficient of friction is 0.25. So the question is to determine the suitable diameter for a solid shaft, assuming the torque on one pulley is equal to the torque on another pulley. So the material for the shaft material is carbon C15 steel, for which sigma y is equal to 235.4 MPa and sigma u is equal to 425 MPa. Here we have to use the ASME code for the design of shaft. Also, we have to consider the minor shock condition. So first of all, let me draw the space diagram as per the numerical. So here, this is the shaft. So this is the direction of view. So here you have two bearings. One is the left bearing and the other one is a right bearing. So this is LB and this is RB. So here you have one pulley. So let me use a different color for that. And that pulley is of diameter 500 mm. And it is at a distance of 200 mm. And you have one more pulley of 300 mm. So you have one more pulley of a diameter 300 mm. So let me place it here, and this pulley is at a distance of 300 mm. Is at a distance of 300 mm. And the diameter of this pulley is 300 mm. And this is your pulley 1 and this is your pulley 2, and the distance between these two pulleys is 500 mm, and the overall distance between these two bearings is 1 meter, that is 1000 mm. So when I view from the left, so here I can see this shaft. So this is our design shaft, so let me hatch that. So I can see the pulley of 500 mm. So let me place that. Here. So next I have one more pulley, and which is 300 mm and which cannot be seen. So let me use the dashed lines. So directly behind, below this pulley, you have one more pulley, and directly in front of this pulley you have a motor. So this is your driver and this is the driven. Pulley 1 is your driver and pulley 2 is the driven. We will assume here the driver pulley is rotating in the clockwise direction, so as the driven pulley will also rotate in the clockwise direction. So the tensions on the driver pulley will be T1 and T2. The tensions on the wheel drive on the driven pulley is T3 and T4. So this is the space diagram. This is denoted as SD. So right below the space diagram, we will use some space for drawing the VLD and HLD diagrams. So let me leave some space. And let me start the calculation part. We know that according to maximum shear stress theory, the diameter of the shaft, the diameter of a solid shaft subjected to combined bending and torsion. If you refer to the data handbook, volume 1, equation number 14.12. So we have the equation here. According to maximum shear stress theory, D is equal to 16 by pi tau ED kb mb whole square plus kt mt whole square half to the power and 1 to the power 1 by 3. So 14.12. So let me note on the equation there. So therefore D is equal to square bracket 16 by pi tau ED floor bracket small bracket KB MB whole square plus KT MT whole square. Close this floor bracket to the power 1 by 2 to the power 1 by 3, and this is equation 14.12 volume 1 from Dr. K. Tingaya data handbook. So in this equation, first let us find the tau ED. So as per in the numerical, it is asked to use the ASME code. So let me use the ASME code. So as per ASME code, American Society for Mechanical Engineers, the tau ED value is found out by using 0.3 times into sigma y. So in our introduction session, we have given the clear information regarding the ASME code. So if you have any doubts, please visit the video and have a look on the information. So that is 0.3 into 235.4 is equal to 70.62 Newton per mm square. The description for the previous video will be shared in the link, or the link for the previous video will be shared in the description. Tau ED is equal to and 0.18 times sigma u. It is 0.18 into sigma u is 425 MPa, so that will be 76.5 Newton per mm square. So among these two values, this 70.62 is the minimum among these two values. 70.62 is the minimum. So therefore tau ED value will be 70.62 Newton per mm square. Also, since the keyway effect is to be considered, as per the ASME code, the value has to be reduced by 25%. The value has to be reduced by 25%. So therefore design a tau ED value will be 0.75 into 70.62 Newton per mm square. So that will be 52.96 Newton per mm square. So this is our design shear stress. Now come back to the equation. So in this equation we have two more unknowns, KB and KT. So let us find KB and KT. These KB and KT are the shock and endurance factors. So for that we have to refer to the data handbook table number 14.2. Refer table number 14.2 for KB and KT values. Here the condition is given as a minor shock condition. So open to the data handbook. We have a table 14.2 where for a rotating shaft the minor shock condition. Here you can see the suddenly applied loads, minor shock conditions. So the range is for KB is 1.5 to 2 and for KT is 1 to 1.5. So let us find the KB and KT values. So therefore, for rotating shaft, and minor shock conditions, KB is equal to 1.5 plus 2 divided by 2. It is an average since it is given a range 1.75. Similarly, KT, it is 1 plus 1.5 divided by 2 is equal to 1.25. So those are the values for KB and KT. Now we'll find the maximum torque in the equation. So come back to the equation. Here we have to first find the KB, KT, then we have to find the MT, maximum torque, then we have to find the maximum bending moment MB. So let us find the maximum bending moment. Now we will find maximum torque MT. Consider a pulley drive here. Consider pulley drive at B. Before I proceed further, let me mark the values on the indications on the shaft. So here this is A, this is B, this is C, and this is D. So for reference I need some indications. So those are the 4 A, B, C, D. Okay, let us proceed. So here consider the pulley drive at B. Therefore the maximum torque at first pulley is equal to T1 minus T2 into radius of the pulley 1. Also we know that the ratio of tensions T1 by T2 is e to the power mu theta. Since the given value T1 is equal to 3000 newtons, also the coefficient of friction mu is equal to 2.24 and theta is given as 180 degrees. So let us first convert the theta, which is in 180 degree, into radians. 180 into pi by 180. So the theta will be 3.142 radians. So initially we have to convert the theta into radians. So therefore I can write the value here, that is 3000 Newton divided by T2 is equal to e to the power 0.24 into 3.142. So on solving I will get T2 is equal to 1411.32 newtons. So therefore maximum torque MT1 is equal to 3000 minus 1411.32 into radius of the pulley, and that is 250 mm. Since the diameter of the pulley is given as, first pulley is given as 500 mm, so the radius of the pulley will be 500 by 2, so that is 250 mm. So hence I can write the MT1, the maximum torque on the first pulley, it is 397.170 Newton mm. When calculating, I'll get that maximum torque value. So remember, the condition is given the given condition, the torque on first pulley is equal to torque on second pulley. Torque on pulley 1 is equal to torque on pulley 2. That is MT1 is equal to MT2, and that is equal to 397170 Newton mm. Now let me consider the pulley at C. So therefore the torque MT2 is equal to T3 minus T4 into radius of the pulley 2. Since the torque we have 397170 is equal to T3 minus T4 into radius of the pulley is 150 mm. As the diameter of the pulley is given as 300 mm second pulley, so therefore I can write the radius of the pulley as 150 mm. So I can get a relation between T3 and T4 is equal to 2647.8. So let me mark this as star. As we know that the coefficient of friction 0.24 and the angle of contact theta is equal to 180 degree is same for both pulleys, So therefore I can write the ratio of tensions T3 by T4 is equal to e to the power mu theta. That is T3 by T4 can be written as 2.1256. So or I can rewrite this as T3 is equal to 2.1256 into T to the power T4. So that is the condition for T3 and T4. So here we have the relation T3 by T4, and now I substitute back into the equation which is indicated as star. So therefore I'll get 2.1256 into T4 minus T4 is equal to 2647.8. So therefore I will get T4 is equal to 2352.2 newtons. Also I can get the T3 value is equal to 5000 newtons. Now let me draw the torque diagram in the above figure. Since I have all the torque values, so let me draw the torque diagram. So I'll consider a straight line, and the points are A, B, C and D. The torque between B and C is MT is equal to 397170 Newton mm. So let me proceed further. Now to find the maximum bending moment. Now to find maximum bending moment, MB. As we remember, in the above equation 14.12, we have only one term that is unknown is MB. So let us find MB now. Once we get all the values, then substitute back into the equation, we'll determine the diameter of the shaft. To get the bending moment, let us draw the vertical load diagram VLD and horizontal load diagram HLD. So let me consider the first pulley. Consider first pulley P1 at B. Therefore, total vertical force on the pulley is equal to T1 plus T2 plus WP1. As you can see here in the three-dimensional figure, so this is your T1 and this is your T2, the tension in the belt. So all are acting downwards, so therefore the net vertical force, so I can denote this forces here. This vertical forces, these are vertical forces and these are your horizontal forces. So the net vertical forces on this design shaft, this is your design shaft, on this design shaft the net vertical forces will be T1 plus T2 plus WP, as all three are acting downwards. So therefore I can write that the vertical force will be T1 plus T2 plus WP1 in this direction. So that is a 3000 Newton plus 1411.32 Newtons plus, as the weight of the pulley is given as 1000 Newton, so let me write that 5411.32 Newtons, and which is acting downwards. Also, the total horizontal force on the same shaft, design shaft, will be equal to 0. As you can see in the figure, there is no any other pulley on the right side or the left side of this pulley 1 which is transmitting the power. So therefore the net vertical force on this shaft considering the pulley 1 will be 0. Now let me consider the pulley at C. Now consider pulley P2 at C. Total vertical force or the net vertical force on the shaft will be just WP2, that is which is acting downwards, as the weight of the pulley is given as 500 Newtons. Also the total horizontal force HF on the second pulley will be T3 plus a T4 in this direction, so that will be 5000 Newton plus 2352.2. So the net horizontal force will be 7352.62 Newtons. So I can see in the figure, three-dimensional one, the second pulley, the weight of the vertical force is WP2 and you have the horizontal force as a T3 and T4 in the horizontal direction. So the net horizontal forces on the second pulley will be T plus T4 and the net vertical force will be 500 Newtons. Now let me draw all these values on the VLD diagram and HLD diagram. So let me take the points here. Let me extend all this. So this is your VLD diagram, as the points are A, B, C, D. At pulley B, the vertical, this is your torque diagram. TD, and this is your vertical load diagram, and here I have a horizontal load diagram. This is A, this is B, this is C, and this is D. So on the vertical load diagram at pulley B, the force is is 5,411.32 newtons, and at pulley C is 500 newtons, just the weight of the pulley. At pulley B, the horizontal forces, the net horizontal forces will be 0, but at pulley C, the net horizontal forces is 7,352.6 newtons. As you can see here, all the forces are towards the shaft. So it is clearly indicated this vertical force of 5,411.32 newtons is acting downwards on the shaft. So from the view, left view, so those forces will be acting downwards on the shaft like this. Next, at pulley C, we have the weight of the pulley, and that is just acting on the shaft, that is the net vertical force. Coming to the HLD, so we have net vertical horizontal force on pulley B is 0, so there is no force there. Next we have the 7,352.6 Newton, which is acting on the shaft in the HLD. So here these two forces are in this direction. So if the observer is standing in front of this shaft, so these forces, that is a T3 plus T4, forces are coming towards the observer. So please note, any force which is coming towards the observer will be drawn on the shaft, and any force which is going away from the observer is drawn upwards the shaft. So that's a very key point to be remembered. So any force which is coming towards the observer is always drawn on the shaft if the observer is standing in front of the shaft, and any force which is going away from the observer will be drawn upwards on the shaft. So as it is clearly indicated in the HLD diagram. Now let us draw the vertical bending moment diagram. Now let us draw the vertical bending moment diagram. So let me extend these values. So these are your points A, B, C and D. Vertical bending moment diagram. Now let us draw the reaction forces RAV. Let RAV and RDV, so here RAV and RDV be the reaction forces. Let us draw vertical bending moment diagram. So consider a VLD, vertical load diagram. Let RAV and RDV be the reactions at A and D. Therefore, taking moments about A. So any force which is going in the counterclockwise direction are considered as positive, and any bending moment which is going in the clockwise direction, they are considered as negative. So counterclockwise direction CCW is a positive and clockwise direction is negative. So with that sign convention, let me find the reactions. So therefore RdV into 1000 minus 500 into 700 minus 5411.32 into 200 is equal to 0. So therefore RdV will be equal to 1432.26 newtons. So that is your RdV. Now similarly, taking moments about D, that is therefore RAV into 1000 minus 5411.32 into 800 minus 500 into 300 is equal to 0. So therefore the RAV value is 4479.06 newtons. Now consider the HLD. Consider HLD, horizontal load diagram. Let RAH and RDH be the reactions at A and D respectively. So therefore taking moments about A, RDH, here the counterclockwise direction, that is CCW, is taken as positive, and the bending moment in the clockwise direction, they are considered as negative. So therefore RDH into 1000 minus 7352.6 into 700 is equal to 0. So therefore the RDH value will be 5146.82 newtons. Similarly, taking moments about D. So therefore RAH into 1000 minus 0 minus 7352.6 into 300 is equal to 0. So therefore RAH is equal to 2205.78 newtons. So let us mark all these values on the diagram. The reactions will be indicated here. So this is your reaction RAV, and that is equal to 4479.06 newtons, and this is your RDV, and that is equal to 1432.26 newtons. Similarly, on the HLD, RAH reaction at A is equal to 2205.78 newtons, and the reaction DH equal to 5646.82 newtons. So let us draw the vertical bending moment diagram. Vertical bending moment diagram, VBMD. So therefore bending moment at A is equal to 0, because bending moment is force into perpendicular distance. We don't have any distance, though we have a reaction, that the bending moment will be 0. Bending moment at B is equal to the reaction force RAV into 200. So that will be 895.812 Newton mm. Similarly, bending moment at C will be equal to reaction force at VRDV into 300. So that will be 429.678 Newton mm. And finally, bending moment at D is equal to 0. Let me draw the horizontal bending moment diagram. Calculate the moments at the horizontal bending moment diagram. Therefore, the bending moment at A will be equal to 0. Bending moment at B is equal to RAH into 200. So that will be 441156 Newton mm. Bending moment at C is equal to RDH into 300. That is equal to 1544046 Newton mm. The last bending moment at D is equal to 0. Now let me find the resultant bending moment RBMD. So the RBM bending moment at A is equal to 0. The resultant bending moment at B will be the summation and the square root of the maximum values at Bn, from the VBMD and HBMD. So these two forces need to consider, square them and take a square root. 2 square plus 441156 square, and that will be 998548 Newton mm. Similarly, the resultant bending moment at C is equal to, so those two values from VBMD and HBMD, these two values. So that is 429.678 square plus 1544046 square. So 1602717 Newton mm. So among these two values, this is the largest, so this will be our maximum bending moment. And finally, the resultant bending moment at D will be 0. So therefore, so this is the maximum bending moment value. So let us draw the bending moment diagrams next. So here we can see the vertical bending moment diagram, horizontal bending moment diagram, and finally the resultant bending moment diagram are plotted to the obtained values. So you can see the point at C, the maximum bending moment value is 1602717. Let us substitute all the values in the equation 14.12 volume 1 from Dr. K. Lingaya. So upon solving, we will get the value 64.94 mm and approximately it is 65 mm. Recommended diameter of the shaft is D is equal to 65 mm as per the table 14.6 volume 1. So here you can see in the table the value for the diameter of the shaft 65 mm is given here. So that has to be recommended. So that is the solution.